Hi everybody. Well, it's third week already, and this is our first video of week number 3. I'm going to spend the first half of this 20-minute video talking about heating curves. And then the second half of this video, I'm going to start to do I've selected a few homework problems from chapter 1 and 2 that I want to go over so I can show you in person. So let's just get started. First half of this video is heating curves, and this is week 3, video number 1. All right, heating curves. One of two things can happen, first of all, when heat is applied to a substance. If I apply heat to a substance, two things can happen. The temperature can go up, or I can perform a change of state. So if you're not increasing the temperature, then you're changing the state of that particular substance. So it could go from solid to liquid, like melting. Liquid going to a gas is vaporization. Sometimes it's called boiling. Liquid going to a solid, right? That would be freezing. And then a gas changing state and becoming a liquid is called condensation. So when you add heat to a substance or a system, basically what happens is you're either increasing the temperature of that substance or you're doing a change of state, okay? And we're going to see that in the heating curve. Increase in temperature is going to be a positive slope. A change in state would be a flat area of the curve. So what I'm doing here at the bottom of page 1 is I'm sketching a heating curve for water. Water, we know, has a freezing point or melting point of 0 degrees Celsius, and it has a boiling point of 100 degrees Celsius. So on the slanted parts of the curve, this is the heat increasing, okay? I'm sorry, this is temperature increasing as I apply heat. The two flat areas of the curve are when I'm doing a change of state. And for water, those changes of state occur on 0 degrees Celsius and 100 degrees Celsius. So the slanted areas of the curve, you can see we're using the heat equation, Q equals ms delta T, which we've learned about before. And then for the flat parts, we have Q equals m delta H fusion at 0 degrees Celsius and Q equals m delta H vaporization on the flat parts. Now this is a heating curve because I'm adding heat. The temperature is either going up or I'm doing a change of state. If I had decided to go down the curve, that would just be called a cooling curve. So a heating curve is the same thing as a cooling curve, and we'll see more about that as we go through some examples. All right, a few notes on that curve I just drew, and we're going to draw that curve a bunch of times in the next 2 videos, so don't worry too much about it. You'll see it again. A few notes for water. Delta H vap. Delta H vap is the heat of vaporization. That's the heat required to vaporize 1 gram of water from liquid to vapor. And it's in units of either 540 calories per gram or 2260 joules per gram. Now, likewise, down at 0 degrees Celsius, we have delta H fusion. So the heat of fusion is the heat required to convert ice or solid water at 0 degrees Celsius to liquid water still at 0 degrees Celsius, right? These are changes of state, the flat lines on the curve you just saw. All right, and the delta H fusion has 2 possible values depending on your units of heat. It's either 80 calories per gram or 334 joules per gram. All right, now let's take a look at the example. How much heat in kilojoules is required, is needed to melt a 125 gram bag of ice at 0 degrees Celsius and then also raise the temperature of the resulting liquid water to 37 degrees Celsius? 2 things here. First, I'm doing a change of state, and then I'm raising the temperature after I've changed the state. So you see the little X I've drawn on the flat part of the curve? That's where I'm starting. I kind of do XO, right? Like a kiss and a hug. XO. XO. So I'm heating from 0 degrees Celsius ice. Move over to the right, flat line. That's 0 degrees liquid. Then I'm going up the curve until I get to 37 degrees Celsius. So there's 2 areas of this darkened black line. That's the part of the curve that I've done here for this problem. So Q equals m delta H fusion for the first part, and then Q equals MS delta T. Q equals MSAT. So I plug in my values. Q equals 125 grams times 4.184 joules per gram per Celsius times 37 minus 0. Q equals 19,400. So you then apply Q equals M delta H fusion. Add up the two values. You get a total joules required of 61,200 joules. All right, but it didn't want joules, did it? It wanted kilojoules. So I have one last step. Start with what I'm given, put it over 1. 61,200 joules over 1. You got 1,000 joules on the bottom is equal to 1 kilojoule on the top. Cancel joules, I'm into kilojoules. 61.2 kilojoules. I started with 3 sig figs. I end up with 3 sig figs. Okay, this is called dimensional analysis, remember? So 61.2 kilojoules of energy as heat is required to first convert 125 grams of ice at 0 degrees to liquid water at 0 degrees. And then we also are going to raise the temperature of that liquid water from 0 to 37 Celsius. See how there's 2 parts to it? All right. Plenty more examples coming up. Here's another one. A patient arrives in the ER, so this is all the background. A patient arrives in the ER with a burn caused by steam. Steam is water in the vapor phase, right? A patient arrives in the ER with a burn caused by steam. Calculate the heat in kcals that is released. Now released, see that word release? That's the opposite of needed or required, isn't it? So this will be a cooling curve. Same sketch, just going the other way. Calculate the heat in kilocalories that is released when 18 grams of steam at 100 degrees Celsius hits the skin, condenses, and cools to a body temperature of 37.2 degrees Celsius. All right, so the way I read this is that we have steam at 100 degrees Celsius, and then we're going to go, condense means go to a liquid. So we're going to go to a liquid at 100 degrees Celsius, same temperature, and only then we're going to decrease to 37.2. So remember, XO, kiss and hug, start with the X right there, move left to 100 degrees liquid. So the X is 100 degrees vapor or steam. The little dot, the blackened dot there, that is 100 degrees liquid water. And then I go down to 37.2 degrees liquid water. So I have 2 darkened parts here. Okay, and you see how I've drawn the little arrows? That's just letting you know, hey, I'm going down the curve. That's why it's a cooling curve this time. So Q equals M delta H vap. Well, that means Q equals M delta H vap is 18.0 grams times 540 calories per gram gives me minus 9,720 calories. Where did I get the minus sign from? Well, it's released, right? This is cooling. It's the opposite. Heat is released. Q equals MS delta T. Q equals 18.0 grams times the specific heat of water is 1 calorie per gram per Celsius. And then we multiply by the temperature difference. We get our answer. We add up our 2 Q's, and we get our final answer on that last page. All right? So here is the final answer. It's actually on this page. My bad. So adding the Q's together, we got minus 9,720 calories. That's from the phase change, or the change of state from 100 degree vapor to 100 degree liquid. And then the minus 1130 calories was our Q equal MSAT. That's when we went from 100 degree liquid down that curve to 37.2 degrees. All right. Negative 10,850 calories. We convert it to kilocalories. Start with what you're given, put it over 1. 1,000 calories for every 1 kilocalorie, and we have minus 10.85 kilocalories. That's how much is released. That's what the negative sign means, okay? So now we're going to switch gears here. In the second half of today's video I'm just going to kind of go over some homework problems from chapter 1 and chapter 2. Most of these were the homework problems that you were assigned. If there's ever one that you weren't assigned, I'll make note of it. Just means I wanted to go over it. Now, this is a handful of homework problems relating to the upcoming exam 1, which I believe is the beginning of week number 5, beginning of week 5. All right, so we got some time, but I just want to kind of chip away at these. Now, that exam is on chapters 1 through 5. Those are book chapters. Today, I'm just going to go over some 1 and 2 problems because I have the time, okay? So, chapter 125, write each of the following in scientific notation. Okay, look, I'm starting with a certain number of significant figures, right? So for A, 55,000, that's 2 sig figs. I have to write scientific notation in 2 sig figs. So it's 5.5 times 10 to the 4th. 480, 2 sig figs. So it's 4.8 times 10 to the 2nd. 0.000005, 5 times 10 to the minus 6. 0.00014 is 1.4 times 10 to the minus 4th. Same number of significant figures in my scientific notation as there was in my standard notation. All right? Now there's a couple more. 0.0072, 2 sig figs, right? Those are leading zeros. So it's 7.2 times 10 to the minus 3. 670,000, these are trailing zeros, but there's no decimal, so it doesn't count. 6.7 times 10 to the 5th. Now, if I had had a decimal, like I've drawn here, 670,000 with a dot, well, then that's 6 significant figures instead of 2. 6.70000 times 10 to the 5th. See the difference? Whatever sig figs my standard notation is, that's how many sig figs my scientific notation will have. All right, number 28 in chapter 1. Which of the following numbers is smaller? All right, if you know how to do it without changing things, go ahead. I'm going to go ahead and change it. So now we're going from scientific notation to standard notation. 4.9 times 10 to the minus 3, that's 0.0049. 5.5 times 10 to the minus 9th is very small, 0.000000, all these zeros, 55. All right? Remember, the base number for scientific notation has to be between 1 and less than 10. That's why it's 4.9 and 5.5 over there. All right, for B, 1250 or 3.4 times 10 to the 2nd. Well, 3.4 times 10 to the 2nd is 340, which is smaller than 1250. All right, number 10, this is from chapter 2 now. Chapter 2, number 10. How many significant figures are in each of the following? All right, so I'm going to draw some out here. A, 20.60 milliliters. B, 1,036.48 kilograms. And C, 4.00 meters. D, 20.8 degrees Celsius. E, 60,800,000 grams. F, 5.0 times 10 to the minus 3rd liters. 20.60, that's 4 sig figs. B is 6 sig figs. C is 3 sig figs. D is 3. E is 3. And F, I missed it. It was going too fast there, but I think it was 2, wasn't it? All right, number 14, chapter 2. Are the zeros significant? Yes or no? All right, so A is 20.05 degrees Celsius. B, 5.00 meters. C, 0.00002 grams. D is 120,000 years. Let's assume we measured those years, okay? 8.05 times 10 to the 2nd liters. So the first one, yes, those are significant. Those are inclusive zeros. For B, those are trailing zeros in a decimal, so they count. Yes, they're significant. And C, those are leading zeros, and leading zeros are never significant. Now D, 120,000 years, right? No trailing zeros here, so it's just 2 significant figures if you were to report sig figs. Here, the base number, 8.05, yes, that is an inclusive zero, all right? All right, number 16 out of chapter 2 wants us to write each of, 16, chapter 2, write each of the following into scientific notation. So remember, not only do you get the numbers right, but you have to watch out for the number of significant figures that they want you to report it in. If they just say write it in scientific notation, you keep the same number of sig figs. Here we're going to convert these guys to 2 sig figs and 3 sig figs will be our bracket answer. So for A, 5,100,000. B, 26,000 seconds. C, 41,100 meters. D, 0.000820 kilograms. The first one, 2 sig figs, would be 5.1 times 10 to the 6 grams. 3 sig figs would be 5.10 times 10 to the 6 grams, right? So for B, 2.6 times 10 to the 4th seconds. 3 sig figs would be 2.60 times 10 to the 4th. Now, to go from 2 sig figs to 3 sig figs, we don't just simply add a 0, evidenced here in our next one. C, 2 sig figs, 4.1 times 10 to the 4th. And 3 sig figs, 4.11 times 10 to the 4th meters. All right, D, 8.2 times 10 to the minus 4th kilograms, or 8.20 times 10 to the minus 4 kilograms, depending on the number of significant figures they want you to report the answer in, okay? All right, this is chapter 2 from your book, number 23. It wants us to round the following measurements to 3 significant figures. So I'm going to take the measurements given, round it to 3 significant figures. A, 1.854 kilograms, B, 88.2038 liters, C, 0.004738265 centimeters, and D, 8807 meters. E, 1.832 times 10 to the 5th seconds. So 3 sig figs, A is 1.85, B 88.2 liters, C 0.00474, because the 8 makes the 3 round up, 0.00474 centimeters, D 8810 meters, that's a tough one, 8,810 meters, no decimal, okay? E, 1.83 times 10 to the 5th seconds. So that was a rounding problem, all right? Now, number 28 was not assigned, but I liked it, and it's something I would ask on a quiz or exam, so I wanted to go ahead and do it in front of you, show you how to do it. 28 says, perform the following calculations and report the answer with the correct number of significant figures. Remember, we had rules for multiplication and division and addition and subtraction. We had rules for how we deal with significant figures. Now, these are all multiplication and division here. Multiplication and division, you go right to the one that has the smallest number of significant figures. So when I look at A, 400 times 185, 400 is only 1 sig fig. So for A, my answer is going to be only 1 significant figure. For D, I've just chosen randomly to do A, D, and F, it looks like. For D, I see the 3.5 is 2 sig figs. My answer will be 2 sig figs. So for A, calculator 74,000. The answer I report is 70,000. For D, the calculator answers 0.00554308. The answer I report, 0.0055, 2 sig figs. Now for F, I see 3 sig figs is my limiting amount, so the calculator answer, I would convert it to 8.58. All right? Calculator answer is not the way you want to report the answers in chemistry. Pay attention to significant figures. Now, this next one's very similar, except we're going to be doing addition and subtraction, if I remember. Okay? So perform calculations and report answers with the correct number of significant figures. All right, so this one is going to be addition and subtraction. Let's let them set up here. I think I've forgotten to use my microphone today. Hopefully you can hear me. But A is 5.08 grams plus 25.1 grams. Now, this is totally different. You don't look at the number of sig figs and go, oh, there's 3. My answer has 3. For addition and subtraction, go back to the previous videos. In A only goes as far to the right as the 10th place for both of them. So my answer is only going to go to the 10th place, 30.2, okay, grams. For B, collectively, all 3 of these terms in B only go to the second decimal place to the right collectively. So my answer is 189.79 centimeters. All 3 go to the hundredths place together. For C, the hundredths place is where they both go. Okay, so it's 10.318. Hundredths place is my answer, 10.32 milliliters. For D, they both go 4 decimal places to the right, so my answer can go 4 decimal places to the right, 0.0069 liters. The rules are totally different for addition and subtraction. A lot of people forget the addition and subtraction rules because in chemistry, we have a tendency to multiply or divide most of the time. All right, I've just now recognized I don't have my microphone on. I'm going to play this back and hopefully you can hear it. If not, we'll see what we can do. All right, so this is the first video of the 3rd week. All right, there's only one more video this week and it's coming up right after this. All right, so stay tuned.